Yes?
When's our midterm gonna be for this
It's like when is our well, the break starts when what it's like 1 2 weeks before. So probably the week before last before the break
Okay.
could be a good time. It is like so it will be then makes it mid-March, I think, right?
Okay, thank you.
I think the break's the 23rd.
On what?
The 17th.
The 17th? Yeah. Okay, so early mid-March. Yeah.
So you're leaving the week before that?
The week we'll see, but then yeah, maybe right before the one before that. All right. So I'll try to. So I'll definitely announce it 2 weeks prior. Okay. So what we're looking at now is the last topic, or at least for now, from that chapter about applications of integrals. And in a way, this is a summary of what we have been talking about. So first of all, the average is initially starts with it starts with the numbers, just a bunch of numbers, and then the average is taken to be simply the sum of these numbers divided by how many you got. Okay. Okay, where is it? Okay, so that's a starting point, and then certainly what does it have to do with anything that what we have been doing, special integrals, but actually quite a lot. And the idea is that there's certain averaging happening. Well, there is no actual averaging happening, but the averaging itself, the part about averaging is this. This is the averaging. But it starts with summing it up. So first summation, and then divide by the number. So whatever that averaging is, the step number one is summation, to put everything together. So that already suggests that maybe it does have something to do with what we have been doing, because we have been adding things together. Okay, it only remains to figure out what is that. How do you average when you have infinitely many quantities to deal with? And the idea is start this way. So we have a quantity, and we think of a quantity spread out over an interval. Okay, specifically, this is a sentence might be still sound puzzling, but really think about, for example, if we're talking about a forest, okay, a forest. Well, let me make it green. You have a forest of trees of various height, and the question might be, what is the average height of a tree in a forest? So these are the trees. Okay, so there's no challenge really to follow the original idea. This is the original idea, and just take all the trees, cut all the trees, or at least measure every single tree in the forest, and then divide by the number of trees. They add together the heights and then divide by the number of trees. Okay, so that is very impractical. However, so one way to do it is to sample it. And sample what? Sample the height. So instead of add all heights, divide by the number of trees. So that's the original idea. So instead of what do we do? Sample heights in different locations. Okay, sample heights in different locations and then deal with the problem that way. So maybe you already recognize what's going to be happening. You cut the forest into smaller parcels, and in each of these parcels you sample a height. Well, it might be even sufficient to sample to look at exactly one tree. Okay, so certainly we're talking about approximations, but you can imagine that, as we have done so many times, you can imagine that if the parcels are small enough, the variability of heights within the parcels will be negligible, and we can really assume that our approximation is acceptable. Okay, so the quantity spread out over the interval is then, in this particular case, is the height. The height, or, well, if you want to think about it, you can also think about the length. And what actually is happening here is how we proceed from the sampling idea to as an alternative. So this one I'm talking about. It is kind of predictable that you just take the sample of the heights and then divide by the number of parcels. But what if the parcels have different size? Okay, so it just happens that maybe you don't have any control over the size of the parcels, so you might end up with parcels that have different width, like this, and maybe another one, and another one, and another one like this, and then one more here. Okay, so parcels might have different width. So what is the answer? How do you then compute the average? So instead of so the plan is still the same, even though we're sampling the heights. The plan remains the same. So we proceed on to say that add the heights and divide by the number, not divide the number of trees, but the number of parcels. Okay, but the plan is still the same. The formula at the top is still applicable. So this formula is still applicable. Okay, so instead now this time x1, xn are the sampled heights. So what if, once again, what if the parcels are different? So what do we do? Right, that's right. So the bigger parcel, the bigger weight should be assigned to, the more weight, almost literally, should be put on the information that comes from that particular parcel. Okay, so that orange parcel, the first, should have, say, twice as important as this one, because it's twice as long, twice as large, so it should be weighed twice. Okay, so indeed the term that we use here, this is called, so use the weighted average. So what is the weighted average? You are in fact familiar with that, I'd say, intimately. Where else do you see weighted averages? In the everyday life? Let me find it for you. It's spelled. Okay, so this is the syllabus. This formula looks familiar. Computing the total score, whether it is your GPA, or it is total for this class. There are different assignments, different part of the grade, but they have different weights. Okay, so the different weight here, as you can see, the midterm percent quizzes 25%, meaning online, project 20%, midterm 20%, as you can see. So the final exam, for example, is worth 30%, which is 50% more than the midterm. Okay, and that respectively is reflected in the formula. Okay, so it's exactly the same story. As you can see, what's important is to understand weighted averages is that those weights have to add up to 1. Look at those numbers. They're, the ones they use in the formula are the same as those percentages you see at the list above. Okay, so 5, 25, 20, 30, 20, 30 add up to 100%, and that is why those decimals add up to 1. Okay, so in other words, this is what we are talking about. So the weights are M1, M2, Mn. Okay, so what is so special about that? Those, they have to add up with 1. M1 plus M2 plus Mn. Mn is equal to 1, and then the weighted average is the sum M1 x1 plus M2 x2 plus Mn xn. Okay, so so like I said, if x1 is more important than twice as important as x2, then M1 will be twice as large as M2. Okay, so either it is a parcel or twice as large, or it is an assignment that is weighed twice as considered twice as important as the next one. So they appear here in that manner. So the percentages, however, have to be looked at carefully, and so that's why they have to add up to 1. Otherwise, it's not weighed, but rather, well, you might end up with larger numbers than you want. So in particular, the regular average, how do we get the regular average, the one that we started with? How do we get the regular average from the weighted average? Look at the formula at the top, x1 plus xn divided by n. How do we get it? What are the weights? What? 1 divided by n. So m sub k is equal to 1 over n. Same for all. So in other words, that is the case when all the parcels are equal, or all the assignments are equal importance. You just divide by n. But in general, you do a weighted average. So you could probably think of other examples of weighted average. But our interest is specifically to be when the quantity is spread out over some interval. So it's kind of a geographic problem in a sense. So when you talk about, say, assignments, there is no particular order that makes a difference. I could rearrange the have midterm after the final exam. That would make any difference, and the result will be the same. So these are just purely numbers that are given to you in the form of a list, and that list can be rearranged. However, our interest is really, as I said, something geographic. So quantity is spread out over some geographic area, such as the forest, and the heights of trees is spread out around that forest. Okay, so then let's ask ourselves, what is then the meaning of should be the weight be when? So what should the weights be if say if the heights are sampled on these parcels of possibly unequal length. So we will be talking about length. So certainly for forest, you probably want to talk about parcels actually making up some squares or whatever. But let's say we are facing exactly what we see here. So the trees are spread out over an interval. Okay, so because we're still stuck with the functions of one variable, so that is we're dealing with the dependence. The independent variable is within the interval. So maybe from A to B. Okay, so then the weighted averages will be, well, the answer should, what should those weights be? Well, so as I said, the weight should be proportional. It should be proportional to begin with to the area or length of the parcel. So once again, twice as large parcel, twice as much weight put on the information that comes from it. Okay, makes sense. Now, but what is exactly should be that number? Proportional is not good enough. Well, suppose, so we have these parcels, and delta x1, delta x2, delta x3, delta x4 are the lengths. Okay, so I cannot take these values as my weights, even though those are the simplest choice would be simply take delta x, delta 2, the lengths of the or areas of my parcels in order to evaluate, to put a weight on the data from each of them, but they would not necessarily add up to 1. Okay, so what should I choose the weight to be in order for them to add up to 1? I have to scale them. I should scale. They might be each parcels may be 100 square feet or just feet of length. So that will not add up to 1. So I have to talk about percentages, right? So a percentage of each parcel from the whole forest. So they are proportional to begin with. So the weights are the percentages or shares of the sizes of the parcels relative to the whole forest. Okay, so you just take each delta x1, for example, is divided by the whole length, which happens to be simply b minus a. So that is what, let me put a k here. So this is the kth weight. M sub k is proportion of the size of my parcel relative to the whole forest. Okay. So once again, referring to this picture, collect information from each of these intervals. Each of these intervals have a length of delta xk, and then to find the proportional, this is what we end up with. Indeed, to confirm, you just take the sum of delta x1 over b minus a plus delta x2 over b minus a plus delta xn over b minus a if you have n parcels, and then what do you have? You have all the sum of the lengths of these intervals divided by the length of the whole interval. So b minus a over b minus a is equal to 1 as required. It is indeed, we are justified in using these numbers as the weights. Okay. Okay, so then what does it give us? So the weights have been chosen. We confirmed that they are indeed add up to 1. So now where is our actual weighted average? And this is what we have. So the weighted average then is average. Well, almost the same sum as I have over there, except now it is multiplied by f of, say, C1. So that is my sample. I sample the length. My function will represent the heights of the trees. And C1 is the location. So sample location. Okay, and then in the first parcel, and then I do the same in the second parcel. And then I have, so I do it n times. So once again, these are all sample locations chosen at random. Once you have all the parcels, the particular choice of samples won't matter that much, because the assumption, your assumption is anyway that is going to be that it's going to be the parcels are so small, then there is certain uniformity within each of them. So the one sample is sufficient. So once again, those fractions are weights, and the what we're trying to average are these. So we're trying to average the heights. So we're averaging these. The heights. Okay, and so what remains is just to recognize that this is nothing but a familiar Riemann sum of this nature. So I will factor b minus a out, and I end up with this sum, which, as I said, will be a Riemann sum, f of ck delta x k. Okay, so Riemann sum, once again, is, again, we are going through this real life, somewhat idealized, but real life situation, and we end up with, whenever necessary, for the 10th time, we end up with a Riemann sum. The only difference is that the extra term in the beginning. Every time we ended up with an actual Riemann sum, and this one, the Riemann sum with this divided by b minus a. So if you think about it, so then what is the meaning of this expression to begin with? We can go back to the same picture that we used every time when we talked about Riemann sums. Okay, so every time when we talk about Riemann sum, that's what we observe. So you can imagine that on the integral AB, we're looking at this forest. It is given this is the forest that is sort of presumes some kind of continuous change of the heights. Then what do we do first? We cut it into parcels. That's the second image. Then possible different weights if it is necessary. Then we pick the sample points and we sample. That is the third picture here. These are my sample points. I sample my heights. So these are the orange lines, are the heights of a particular tree chosen at that particular location. And then what is the last picture? I multiply that height by the width of my parcel. So just as this Riemann sum indicates right here, that is the height over here, and this is the width. Okay, so that's what we observe here. So what we're seeing is literally what our discussion was about, the heights of trees. So the height of the region under the trees. So I could try maybe to make that point clear. So these are my trees. So no, that's actually not it. This is what I meant. The tree is this, where the function is sampled is where there is an actual tree. So this, if I pick C1, there is a tree of this exact height. Okay, and then I keep doing it. This may be another tree here. So once again, at location Cn minus 1, that is how our tree is. Over here, it is in fact these just cutting the parcels out. So then it is interesting then what we're talking about is literally the areas, because we are looking at literally the heights, and we multiply by the literally the width of those parcels. So these areas are indeed, they represent, they are measured in, say, square feet. So the length times the height, well, it gives you square feet, so no surprise that we end up with a Riemann sum. And where's my thing? With a Riemann sum, and then once that problem is solved, once this realization has come, we take the next step, as we have done a few times by now. We take the limit. So if there is actually there is some kind of theory behind this experiment rather than actual numbers, when you have actual numbers, that formula will be just fine. So the situation I described will be fully covered by this thing. So parcels, different width, and sampling, and all of that works out just fine. The next step is needed whenever there is some kind of theory behind it, and your forest is not actual forest that you see and you're dealing with, but rather there is some kind of theory that forest would look like this under these circumstances, and you are doing entirely theoretical work. Then this function f is an actual function sampled in a literal sense, just like this picture indicates. The function is actually defined everywhere. And then next step is take the limit with what delta xk altogether. They go into 0 and goes to infinity, and the end result is the Riemann integral from a to b, 1 over b minus a, and this is still f of x dx. So this is called the average value of f over interval ab. So this applies to any function. That idea and the definition applies to every function not necessarily representing forests, does not necessarily representing heights, as the initially was suggested. It was just an example. It applies to anything you can think of, and in particular, every example that we have had in this chapter can be interpreted in that way at least a little bit. So, for example, if we're talking about well, one example could be seen right there in the picture here. If we look at the original picture on the left, so forget how interesting. Okay. So if you look at the original picture here, then what we're talking about, you can say that the question might be, what is the average height of under the graph? Okay, so we're talking about this height from here to there, and what is the average height? While there are infinitely many of them. That's why we have to go into this length, into all this trouble. The point is, what if there are infinitely many terms to worry about? So once again, AB, y equal f of x, the average height of the region under the graph Okay, so that's one way to interpret it. So this is, for example, this is a sample, but there are infinitely many of them. At every location there's a number which is different from it. So that's why we need, once again, this formula from a to b, b minus a fx dx. Okay, and how else can we interpret this? The average, how about the average distance to the x-axis from the graph? Same thing. Okay, so another one. So this is a point, there's the distance, and we average them. What else? How about we're talking about the volumes? Remember we talked about the three-dimensional solid kind of located around the x-axis, and then what we did to find the volume, we are did the cross section of that solid with a plane perpendicular to our to the x-axis. Okay, and then the volume is integral ax dx from a to b, if this is b and this is a. Okay, so you integrate the area of a to b of the area of the cross sections. So this is ax. Whenever this is x. Okay, so whenever your cutting is at the location of x, then you compute the area integrated. So we did a few computations with this, but now we can also interpret this in a slightly different way. What we have found, what if we divide by b minus a? So then it's not the volume, but rather what is it? It's the average area. Okay, so that formula for the volume that expressed in terms of the cross-sectional areas, can now be translated and understood in a slightly different way. So what if we keep cutting and we don't really care about the volume to begin with? We just want to know what's the average cross-section is, and that's how you do it. You integrate the area, divide then by the length of the interval. That's what we have here. Same applies to, how about another example that we had? How about the flow? Come on. Nope, nope. Just scroll it. No, scroll. Okay, so I'll just go on. How about the average velocity? We already had that, but now we can think about. Remember this situation: you have a canal, and you have some line we drew in some kind of lock there, and then the velocities, however, vary in length, in magnitude. Okay, so you might ask yourself, how do you understand the average velocity through the canal in a particular location? And the answer is, you realize first of all what that function is. That function is that represents your velocity, and to find the velocity, you just go through the computation that we have. So it will be once again integral from a to b fx dx, and then you divide by b minus a. So in other words, you still remember what f of x is. The integral itself, you still remember what it is. It is the total flow. This is how much, the integral itself is how much water has crossed this line for over a given period of time. Okay, so now we use that just in order to understand what the average flow is. The average velocity is you take the total flow and divide by the length. Okay, so that certainly makes sense. The same thing with work. So once again, if you are talking about, you might ask yourself in a very similar situation, similar illustration, you're moving from A to B, and then there are forces that you have to deal with, and you are asking yourself, in what sense can I speak of average forces? And that's, once again, you do the same thing. If F is your force, AB is your trip, you integrate force over the length of the trip, over that interval, and divide by the length of the trip to average. So that division is what makes it averaging. So if you can compare this with the original definitions, which was of an average, which was summation divided by the number of samples, if you like. But this time, if there is some kind of geographic idea here, and there's a continuous change of that quantity, the quantity is spread out through that interval, just like this one, then the averaging is slightly different. You divide by the length of the interval. So that's what we do every single time when we talk about averages. So divide by the length. In the high dimensions, naturally, if you were actually talking about a forest with spread out on a surface of the Earth, then you're going to be doing the exact same thing, summation, but of a function possibly of two variables. Okay, so but then you divide by what? By the total area of that forest. Okay, so similarly, if you're talking about the density, and which varies possibly continuously throughout the rod or any kind of object, what do? You integrate that density over the whole thing and then divide by what? By either the length, the area, or the volume, depending on what kind of dimension you are dealing with. Okay, so that's roughly how it works. A Riemann sum that produces a Riemann integral, and then it could be helpful for us to understand certain things that cannot be averaged in the usual way. Just one more picture to illustrate what the average is this. Okay, so the idea here is, as you can see, you have some kind of pile of sand, some surface of sand, and then what is the meaning of the average? You take the sand and even it out. Okay, you even it out, that all sand, which might be curved, and that level of the same amount of sand, but leveled, that gives you the average depth of that sand. Okay. So, like I said, so there is some of the areas are too deep, some are higher. So you take this equipment and just spread it out in a totally flat way, as here, and then this level is the average. This one, this distance, is the average height of the average depth of the of this surface. Okay. So there will be a few problems more of this kind in the homework a little bit. In the meantime, so let's see what we have left in this course. Is a little bit more examples of integration. If we have time, I put it off until later. Then we're going to start with the sort of introduction into multidimensional calculus and parametric curves, because it's so important, and it really gives you an opening into studying motion, for example, and that is frequently, in addition to these topics, those motion topics might be your typical topics for your projects. So you probably should already start thinking about your projects. So you've seen the list of projects. There's a link from that page. Let me show you. So so this lectures. So just the basic description of the project, but really you got to click on this over here, and there's a long list of projects. Long list of projects on it. First of all, it starts with the description of how projects work. And then there goes a little list of projects. Some of the projects remain like Calculus 1, so try to stay away from those. And some, however, go beyond Calculus 2, and so they are Calculus 3 and beyond. Okay, so once again, try to make sure they predator-prey, for example, that is differential equations. So try to make sense of these, but just read them at least a little bit, so to start maybe figure out what interests you the most. Okay, so we'll get to that. We'll get to that after the midterm. Okay, another big topic that remains that we'll deal with later is series. So one of the but by far the most challenging part of the course is not actually this multidimensional business, neither integrals nor multidimensional business, but rather series. So we'll get to that in 2 installments, and we'll start what we start next with is sequences, which is something that comes from from calculus 1, except usually it's skipped over pretty quickly. So sequences, and you've seen sequences and their limits. So let me just give you an idea of what I'm talking about. Is say, I don't know, 1, 1/2, 1/3, 1/4, 1/5, 1/n. Okay, so that is a typical example of a sequence. That is a finite sequence, so it has n elements, n numbers arranged in a row. That's what a sequence is. Makes it a finite sequence. You could have an infinite sequence if you keep going. You might keep going, and then the question, well, you have something more complex. But then in that case, usually the question is very, very narrow, and that is, what is the limit of that sequence? Okay, so you already seen sequences limits before. So, for example, if we're looking at the sequence, I suppose it's an infinite sequence, then the question is, what is its long-term trend as n is increasing? So you probably know the answer to that. What is the answer? What is the trend, long-term trend of the sequence? It is going towards 0, and how do you know?
Because n is increasing, but numerator is not.
That's right. So numerator remains 1, and at the same time n goes to infinity. So you divide by a larger and larger number, and so the whole thing is brought down by 0 as a result. So one thing is just to supply this kind of logic as we just did. Another one, you might actually remember something related from calculus 1, and that is horizontal asymptotes. Remember those horizontal asymptotes? So the question is related because, very much related, because we're talking about the graph of a function 1 over x, which is almost the same thing, except there are more points, right? So you have either discrete points like this. That is the sequence I'm talking about. And what I plotted in red is the graph of a function y equal 1 over x. So as you can see, there is much less to worry about. Function 1 over x might have a lot of things that you studied in calculus 1, and so, for example, you can study continuity, you can study its limits, you can study its derivative, you can study its vertical asymptote, bunch of questions you can ask. But if we're talking about sequences, there is one and only one issue, and that is what is going on over here. So if you progress with x from left to right, x goes to infinity, which is the same as n goes to infinity, is the only one question that we ask about this function. What is the long-term trend? Not what's happening in the middle. Whatever is in red is really we don't care about. We only care about those points and what is where those points end up. And the answer is indeed we end up at 0. Okay, so that is one way to look at infinite sequences. Another place that you've seen sequences was Riemann sums. Those were finite sequences. The one that we looked at not too long time ago is you might remember this summation. We had 1 plus 0 plus 1 plus 2 plus 3 plus n is equal to n plus 1 over 2. Okay, so that is once again this is also a sequence. Or rather, the sequence, this is the sequence. The numbers are sequences. It is when we sum them up, we end up with either a Riemann sum. This could be a Riemann sum under certain circumstances, or we end up with series. Okay, so the series, we will postpone series until later, until we are comfortable with sequences, because there's a danger of skipping too quickly from sequences to series, and then the summation that is so crucial to the whole computation over here is really lost. So this is what makes it a series. summation makes it series. It's what makes it, or even sum, but primarily the series. So for example, I could still start adding this up and see what happens, and the result would have nothing to do with 0, because just because you're adding numbers small and small does not mean that you will end up with 0, or well, it doesn't say anything to us. Okay, so let's look at the sequences, starting with a few examples. Okay, sequences. So a sequence is a function nothing special. So it's still a function. We still study functions, but this time the input is an integer. So this is how it actually manifests itself. It manifests itself as what we have done even recently is subscripts. Something that you need to get used to, and that is what I did already a few times: x1, x2, xn. This is what I did today, and that is exactly so. We did at the very beginning. We did the average of n numbers. So what does it mean? It means that you have these are real numbers. And you can just say these are real numbered, or how should you put it, listed or marked with those indices. So these are the subscripts. So they indicate the order of that number in the sequence. So the place of x sub k, say, in the sequence. Okay, so so kth place, so first, second, third, and so on, and we'll put it as a subscript. But it is still the way, if you want to have a general view on functions, you think of these numbers as inputs. So 1, 2, 3, and so on, n are the inputs. Okay, and x1, x2, xn are the outputs. So if you think of it this way, then you realize that this is indeed a function. A function with, as it frequently functions are represented by, they are represented by tables with one row made of those of the inputs, and one row of the outputs. Okay, so I guess I'm out of time, and so we'll just continue to more about sequences.